Okay, we begin our next seminar, and today our speaker is Professor Manuel del Pino from the University of Bath. Please, Manuel.
Okay, thank you very much, Alexander, for the invitation. So very happy to participate in this seminar. So the topic of my talk today will be a problem that is relatively classical in calculus of variations. I will explain it. It's not hard to say what it is about. It is a problem that originates in a model in nuclear physics. With the concerning my own knowledge of the model is not much, okay? but the problem will have elements that I think will be familiar for most of you. So let me okay, so this is called the liquid drop model, okay, due to famous physicist Gamow in 1928. Okay, so this is a variational problem. The problem is finding critical regions omega. Omega are bounded regions in three-dimensional space that are in a certain sense critical for this energy functional. This energy functional has two components. One is the perimeter of omega, which means in some weak form, okay, the area of the boundary of omega. So this is what we have to think of. This is like the area of the boundary. Plus this quantity, which is a summation, say, of interactions between Coulombian interactions between points in omega. Okay, so that's the meaning of this. Okay, so as I mentioned, then the perimeter denotes simply the area of the boundary when, at least when omega is smooth. Okay, and in this Gamow's critical liquid drop model, this energy represents the energy of an object called a nucleus. Okay, and a nucleus is by definition a collection of nucleons, and these nucleons are assumed to be either protons or neutrons, okay, that are uniformly distributed somehow in the inside the region omega with a constant density, okay, so kind of uniform distribution in the inside omega. Therefore, we can think of that the volume of omega is a quantity proportional to the total number of nucleons, okay? So assuming that this distribution is uniform. Okay. So here I write the energy again. So the energy is the perimeter plus 1/2 of this sum of Coulombian interactions. In the energy term, the perimeter of omega represents an effect of surface tension, okay? Somehow this surface tension wants to hold the nucleons together, okay? So somehow you don't want that this perimeter become too big, okay? So it's so the effect, the expected effect is a reduction of the perimeter, some minimization effect, okay? While this other guy, okay, represent Coulomb repulsions among the nucleus. So the total Coulomb interactions that are repulsive, okay, among these objects, the nucleus. Okay, so perhaps the difference between one quantity and the other is that this one involves points of the boundary, right? While this one involves all points inside the region. Okay, so what are we interested in? What we would like, here I will formulate the problem I want to work on. What I would like to find is stationary regions for this energy under a volume constraint. Okay, so I will assume in what follows that the volume constraint is given by like this, but volume is equal to some specific prescribed number m. And what I would like to find are regions omega that are stationary or critical for this guy, for this energy, when subject to the volume constraint. Let me give you an example, okay? In case, how can we find such critical points, okay? Say the basic example would be ground states. What are ground states? For a given mass m, correspond to solutions of this variational problem, the problem of minimizing the energy subject to the volume constraint m. Now, let me tell you what it is known. I will make a certain historical review about the problem that has a very nice recent contributions too. It turns out, yeah, I will try to give you an idea of why this is the case, that when the mass is sufficiently small, then there are minimizers of this object, okay? While these minimizers do not exist if the mass we are prescribing is big, okay? They could be, maybe there are regions that are local minimizers, but global minimizers definitely don't exist for large m, okay? This is the case, while they do exist when the mass is small. So the stationary problem amounts to finding omega with vanishing first variation of the perimeter with respect to normal perturbations of the boundary that preserve the volume m. In the smooth case, I will review for you in a little bit later while this is the case. It turns out that the problem of critical regions or critical points of the energy correspond to finding the region omega such that this relation holds. So a relation of this form holds for all x in the boundary of omega. Where, what are these guys? This is just the mean curvature of the surface, partial omega of the boundary of omega at the point x. And this one corresponds to the derivative of this Coulombian interaction. And what we want is that the sum of these two guys is equal to a constant, okay? And this constant is not prescribed, it's a Lagrange multiplier, okay? That arises from the fact that we are imposing among the perturbations that we are taking for omega, and when we take first variation, we want to do them in such a way that the volume is preserved to be m. Okay, this problem itself has an interesting history. Let me mention a problem that perhaps is more standard, okay? Which is the problem of finding regions that have constant mean curvature, okay? Constant mean curvature correspond to essentially to critical points of perimeter subject to the mass constraint, to the volume constraint, okay? And in that case, we ignore this guy, okay? But this one, which is the correspond to the derivative of perimeter, in fact. Bohr and Wheeler, by the way, introduced this equation, this problem, or the variational problem. The variational problem was probably introduced before, but Bohr and Wheeler introduced this specific problem to compute the minimal energy required for nuclear fission, okay? This is the physical context for it. Okay, so I write for you the energy again. I call sometimes C of omega this Coulombian interaction part of the energy. And here is the first variation equation equal to a constant, which is which corresponds to the Euler-Lagrange equation for that constraint variational problem. Let me observe for you the following, and this is kind of interesting. Balls with volume m are always critical points in this sense, okay, in this constraint sense. Why is that? Because they are critical for both the perimeter and the Coulomb interactions. Why a ball is critical for the perimeter? Well, a ball has constant mean curvature, right? So this guy here is constant, yeah? Not only that, actually from the classical isoperimetric inequality, balls are precisely the minimizers of perimeter with prescribed volume M, okay? Balls of volume M will be the minimizers, okay, for the perimeter part. But you can also observe the following. If you insert here a ball, okay, and you evaluate this quantity at points of the boundary of the ball, this quantity, because of the invariance under rotations of the integral, okay, turns out to be also constant, okay? This quantity is constant in a ball, okay? So we are in a rather surprising case, okay? We have that this guy is constant and this guy is constant. Obviously, the sum is constant too. However, as critical points of each of the components, balls have a very different nature, okay? It turns out that balls minimize perimeter with prescribed volume. However, they turn out to maximize the Coulombian interactions, okay? So if you put a ball here, you have the highest possible interaction among regions with volume M, okay? With given volume M. Okay. Here is what I was saying, the classical isoperimetric inequality in this version for the perimeter definition as given by the Georgi, okay? I mean, the classical versions of this are probably come from much earlier, but this is the situation for the definition in terms of variational calculus of variations. So the perimeter of a ball of volume M is the minimizer of the perimeter among all regions with volume M. And therefore, of course, the mean curvature of the boundary is constant, okay? On the other hand, there is a result by Rees in 1930 that states what I was also saying, that the volumes, that the balls with volume M actually maximize the other guy, the Coulombian interaction part, yeah? And that implies that this is also constant, okay? And we end up with the with this relation satisfied, yeah? And this in a ball. Here I meant for all y in the boundary of the ball. Okay. On the other hand, what I was saying, the two terms in the energy describe opposite effects, okay? Because for balls turn out to tend to minimize perimeter, but tend to maximize this Coulombian interaction. So we may wonder about the nature of the balls as critical points of this energy, for instance. And even more delicate, the question is how to find non-trivial critical points, okay? Non-trivial critical points would be, I mean, it's not clear at all that there will exist minimizers of this guy, okay? So if we want to find critical points, we should find them in a different class of fields. And this is not so easy for several reasons. Imagine that we don't have this Coulombian part, but only the perimeter, okay? So solutions of the problem, if the energy was only the perimeter, would be constant mean curvature surfaces, yeah? And constant mean curvature surfaces that are compact and nice, namely embedded. This is a classical result by Alexandrov in the 1950s. Must necessarily be balls, okay? So there are not really compact, interesting critical points for the perimeter once we are in that setting, okay? however, it is not to be discarded that maybe this guy does have other compact critical points. Okay, I will try to justify for you an assertion that I made at the beginning. This is not a full justification, but at least provides some intuition on why for small mass m, it is plausible that there are minimizers of the full energy, while if the mass is big, this should no longer happen. The reason is very simple to state. It turns out that for small volume, the perimeter part in the energy turns out to be dominating compared with the Colombian part, okay? So you might think, okay, well, the functional is a small perturbation of this perimeter functional, and the perimeter functional has a minimizer, which is a ball. And therefore, if we perturb it with a comparatively smaller guy, the minimizer should still exist, and even hopefully be balls too. And part of this is known already, in fact. So let me play the following game. Let me write omega as m, which is the prescribed mass. When I mass and volume, I use in an exchangeable way. Okay. If I consider omega written in the form m2 power 1/3 times e, okay, then having volume omega equal to m is equivalent to having volume of E equal to 1, right? I mean, the scalar is raised to power 1/3 because the volume of alpha E, okay, is alpha cubed times E. So I need to take alpha to be m to power 1/3. Now, if I actually define alpha by this relation, m times alpha equal to m to power 1/3, then I get the following. First, the perimeter of alpha E. So if I dilate, multiplying by alpha, the quantity E, the area of the boundary is grows proportionally to alpha, but not to alpha, but to alpha squared. Okay? So we have the validity of this relation. While for the Coulombian part, it is also to track what's going on. The Coulombian part of the region alpha E can be written as this integral, right? But I would like to take this integral into an integral on E, or on E times E, actually. And if you do that and replace in this double integral, you make the change of variables, changing x into alpha x and y into alpha y. Then I get this. The Coulombian of alpha E is this guy, okay? And what is alpha to power 6 over alpha? Okay. This implies that we get the following thing. For the perimeter, there is alpha squared coming out. And for the Coulombian interaction, there is an alpha to power 5 coming out. So there is a discrepancy of 3 powers of alpha between what comes here and what comes here. If I divide by alpha squared, which means multiplying the energy by m to negative power negative 2/3, then I get the perimeter of E, yeah? And here I get m, precisely m, times the Coulombian interaction, the Coulombian term for E, okay? So you observe what happens. What the problem of minimizing this functional for volume equal to 1 is equivalent to minimizing this quantity for E, and it is to be expected that if the m is small, then this term will have a lower order influence, and then the perimeter should be the leading order term, okay? So this is why I say here, this suggests that for any mass m sufficiently small, there is a global minimizer, while for m large, there are no global minimizers. Why? Well, because remember that balls, first of all, are for the Colombian part are maximizers, not minimizers. It's exactly the opposite, okay? And if the M is big, okay, then the Colombian part will be the dominant one, and then it is to be expected that no minimizers are present. Maybe maximizers, but that's also hard because you have perimeter here. So it is not clear what is going on for M large, while for M small, it is expected that minimizers exist. Let me consider yet the following key number, okay? A number that I will call M star. I will explain you in a moment what this number represents. This number M star, defined by this critical thing, okay, that this exact number, which is approximately equal to 3.51. This value for the mass is the value of the mass M for which the energy of one ball and that of two balls with half the corresponding mass located at an infinite distance become equal. Okay, let me go here again. Okay, here is the Colombian interaction and here is the perimeter. So what this mass represents is the value M, okay, for which if omega is the set consisting of two balls with volume M halves each, okay, and you put them at very large distance, say infinite distance, one from each other, then the sum of these two things is equal to the energy associated to one ball of radius of volume M. Okay, so this is what it is said here. This is the ball, okay, with volume. This ball here is the ball with volume M star. Okay, this is what is here. So the energy of a ball with volume M star is equal to 2 times the energy of this thing. Okay. When you consider the centers, okay, going to infinity, from one ball to the other. So look at what we get. What we get then is that we have precisely this relation here. Now, concerning the value of M star, there is a conjecture traced stated in 2011 by Choksi and Pelletier. What they conjectured was that if the mass is less than M star, then the infimum is attained precisely when, and moreover, precisely when omega is a ball. While for M bigger than M star, the infimum is not attained. Okay, this is the conjecture. There is something we can be sure about immediately. I didn't show you the computation, but when M is bigger than M star, it turns out that the energy of two balls, okay, is in reality lower than the energy of the single ball, okay, and then balls are no longer minimizers. This we can be sure, okay, because two balls at a large distance one from each other will have a lower energy than the energy of a single ball with radius M, with volume M. Okay, so this is the situation. However, it is also conjecture that if M is less than M star, then the infimum is attained, and not only is attained, but it is attained precisely in a ball. Okay. So here, let me show you what is known, what is rigorously known, rigorously proven. Okay. First, it is known the following, that there exists a number M1, which is strictly less than M star, yeah, sufficiently small number M1, such that whenever the mass, the prescribed mass, is less than M1, balls are minimizers, okay? So for sufficiently small ball, in summary, for sufficiently small volume, balls are minimizers. And this was proven by three works, independent works. I don't know if totally independent, but they appear in the same year. Nuffer and Muratov, Julin, and Bonaccini, Cristofori. Okay, in these three papers. Now, something that it was proven by Rupert Frank and his collaborator Nam in 2021, so many years later. They established that when m is less than or equal to m star, there exists a minimizer. Okay? So minimizers exist. So if you are below this critical mass that I mentioned before, there are minimizers, but we cannot say that minimizers are balls. Yeah? They established that minimizers exist. And you remember m star was 3.51 approximately. They also proved that if m is bigger than 8, no minimizers exist. This was proven by Frank, Kilip, and Nam in 2016. So this is what is known in this setting. Let me mention that people have also worked the case of other type of risk potentials, for instance, originated from inverse of fractional Laplacians, and also with the fractional perimeter. Okay, I mean those that lead to minimal surfaces, fractional minimal surfaces. This is the work by Figali and Fusco. So I mentioned these works while they are not directly related with the context that I am describing, but I think these are important works too. Okay. Okay, so in summary, what do we know? We know that balls are minimizers for some number m1 to the left. Okay. Now, if you are between 0 and m star, yeah, it turns out that in this range you can still say that there exists a minimizer. Okay, except that you don't know if minimizers are balls while this has been conjectured. On the other hand, if you are above m star, balls are definitely no minimizers. This is easy to establish. It's a direct bound. And besides, this is the other thing that we know, that for mass bigger than 8, there are no minimizers. Okay, this is what was proven by Frank, Kilip, and Nam. Oh, and let me show you yet another number, the number 10. Okay, the number 10 is a very special. It's a very special number. It is the number where balls lose stability. Okay. I mean, from 8 and on, there exists no minimizers, simply. In fact, and balls are no global minimizers beyond m star. However, they could still be local minimizers, okay? It turns out that they are local minimizers. The balls are local minimizers up to mass equal to 10. And beyond 10, they are no longer stable. So they are no local minimizers anymore. Yeah. So this is a fact, and this is also relatively simple computation. So balls lose stability, okay? They are stable up to 10, and beyond 10, balls are no longer stable. Solutions. Now the question is, can we find interesting solutions, hopefully compact, bounded solutions to the problem P with a large mass, which are not necessarily minimizers? I mean, from here on, in fact, there are no minimizers simply, yeah? But here is the question. Can we find other solutions, not just balls, that are solutions to our original problem? This is the context. Okay, let me mention to you some known facts concerning the loss of stability. Some more geometrical fact with a little bit more geometrical flavor. The ball loses stability when the mass, sorry, this notation actually corresponds to a paper by Xu and Du, recent, 2023. And this chi star, this number chi star, please imagine it is the mass, okay? And chi star, the number chi star corresponds to mass equal to 10, and while bigger than this and less than this correspond to mass to the left or mass to the right. Okay, so what is expected, and in fact proven, this was rigorously proven by in 2019 by Frank. He managed to describe in a very precise way the bifurcation branch that stems from the value mass equal to 10 or chi equal chi star, which is the same. And well, I mean, what is the idea? You have the trivial solution that is a ball. However, here there is a bifurcation. Yeah. Say, what do we expect? We expect that, okay, here the guys are minimizers, local minimizers. Then the balls are no longer local minimizers. However, we expect that there is a branch of local minimizers coming from here. Yeah. And the shape this guy have is oblate like this one. So it's so the ball is deformed, making the poles, you know, one closer to the other. Okay, that's the oblate, and the opposite effect is called prolate. And prolate is what you see to the left. You see solutions here. You have the balls here are minimizers, and here you see mountain passes coming out. Okay, that have this shape. Actually, this bifurcation analysis in a less rigorous way was already made by Bohr and Wheeler, okay? But the rigorous result, the rigorous construction of non-trivial solutions with these forms, with this form around the bifurcation value is the subject of the paper by Frank in 2019, okay? This is the situation. Okay, these are other pictures obtained numerically. Yeah, by the way, this paper is numerical. Please don't ask me how they produce these numerics, but this is what they observe. The number chi star, okay, in this setting we have to think it is 1. Okay, the mass equal to 1, then you will see a perfect ball. Okay. In the bifurcation branch. Remember the branches. Balls are here, and to the left you will see something, and to the right you will see something else. I will try to describe you what you see in this prolate-like and this oblate-like. Okay, say the value chi star is like around here. Then what happens with the branch to the left starts developing something that has a form like this, the oblate guy. Okay. Apparently, there is some values at which the solution even loses convexity and starts looking like this, you see? And what we end up having is something like 2 balls, okay, which are connected by a small neck, okay, by a tiny neck. And you end up at the end something degenerating, okay, like two balls tangent. So this is
Manuel,
yes.
may I ask?
Yes.
Am I right that this is because for small mass the main term is just perimeter?
Yes. Let me say something about that, because in fact I think an important point. To the left, so your question is, why do we see balls for small mass or shapes like this? In fact, what you see is something that looks very much like a constant mean curvature surface. But this constant mean curvature surface in full does not exist, okay? say, because of the Alexandrov result. In Alexandrov result, constant Michael measure surfaces compact and embedded must be balls necessarily, just a single ball. However, as you go to the left, you start seeing shapes like this that are compact and embedded. In fact, this is something we have detected too. But essentially, what these guys are, the two balls connected by a small neck, is a piece of an unduloid, a constant Minkelsbach surface. Okay. So this is more or less the intuition behind it, but it is correct what you said. Okay. I mean, the fact that the mass is small makes the perimeter part dominant. Then somehow what you will see, at least locally, are in these critical points are constant Minkelsbach surfaces. I think that's an explanation for it. While when the mass grows, you no longer see this. However, you see kind of interesting shapes. These shapes also lose convexities, and you end up seeing something even that looks like a torus. Okay, with so this is another type of surface. You could also think that this is approximately constant Minkelsbach as well. Okay, but this is the setting. Okay. Okay, let me tell you about one non-trivial solution, very different from a ball, that was already found. This is a solution that is radially symmetric, I mean axially symmetric. Say you have X, Y, and Z, and this guy is a surface of revolution. What was found by Ren and Wei, 2011, was that for every mass, M sufficiently large, there exists an axially symmetric torus-like solution. So a torus, that looks like this. It's not a torus with a circular region. So the section, sorry. The section of this torus is not a circle. It's the same, okay? It is a revolution thing. But the section is not exactly a disk. Okay? It is like a deformed disk. It's something close to a disk, but it's not a disk. What they were able to find also about the shape of these solutions is that these have a large radius. These tori have a large radius of order m times logarithm of m to the power 2/3. Okay, while the radius of the section, okay, which is an approximately circle with a radius that goes to 0, like the log to negative 1/3, okay? And these asymptotics are true with precise constants here, of course, when the mass goes to infinity, okay? So for large mass, you can find solutions with somehow unexpected shapes, okay, like the toroidal one. Let me mention that in any case, that the problem that is solved by this torus guy is essentially a two-dimensional problem, because the problem is one for the section, yeah, and the section is like a small disk, and it is a small disk that satisfies certain equilibrium law, and this is how the solution is found. So it is true, it is three-dimensional because it is a torus, but it is not a truly three-dimensional object what we are talking about, okay? Now, these solutions turn out to be unstable, okay, which is not surprising, of course. However, they are stable under the natural axisymmetric perturbation. So if we consider axisymmetric perturbations of this region, yeah, say it's like small deformations of this guy, the small deformations of the section, I should say, then you see some form of stability. Okay. Some discussion about this can be found in this nice survey paper that appeared in Notices of American Math Society in 2017 by Choksi, Muratov, and Topaloglu. Okay. Sorry, is there any question that you would like to ask? Okay, so if not, I continue.
Okay.
Okay, let me recall what I was telling to Alexander a moment ago. What are the Delaunay surfaces? The Delaunay surfaces, let me remind you, okay, is a family of periodic surfaces of revolution that have constant mean curvature, okay? The constant mean curvature is something you can, of course, normalize, okay? Say that I consider the family of surfaces of revolution with constant mean curvature equal to 2, okay? These guys, actually, you can compute explicitly. You can find a formula for them. A formula that depends on some special functions, but it is originated in the ODEs, in the ODE, which is a second order ODE satisfied by the profile, okay? And what you see is that when this parameter A, what is this parameter A? This parameter A is what is called the next size, okay? When the A is 1/2 means that you are in the case of the cylinder, okay? Because remember the mean curvature is 2. And the mean curvature 2, this mean curvature 2 is what you will see when the next size is exactly 1/2. But when the next size starts decreasing, you start seeing this shape, okay? Shape like this. And as A goes to 0, you end up seeing, when the next size goes to 0, what you see is an array of spheres, yeah? An infinite array of spheres. These guys are periodic and infinite, yeah? Oh, and even more, actually. You can go in this family for even negative parameters, but in that case, what you see are surfaces that are no longer embedded. They have self-intersections, like in this picture. Yeah? I will not be interested in this part of the picture, but actually I will be interested from here and on, here to the right. Okay, so when A is equal to 0, you see the infinite array of tangent spheres. When A is equal to 1/2, you see this cylinder. And in between, you see this topological cylinder with this intestine shape. Okay, here is another picture taken from the web, okay, for the Delaunay surface. What I will fix from now on is a Delaunay surface, sigma A, with parameter A between 0 and 1/2. A, I remind you, is just the next size. Okay, so as I mentioned before, this surface of revolution can be parameterized in the following way. If you label points in space as x bar, x3 in this picture is meant to be the axis. So it's the coordinate of the axis of this guy. Then since these are surfaces of revolution around the axis, then the profile is going to be given by R, okay? This polar coordinate x bar, okay? Absolute value of x bar is equal to a certain function of x3. So for each x3, you see, this is just the equation of the profile, okay? This is the f. This guy is f of x3, and x3 is the horizontal thing. These guys are also periodic, okay? And have a certain periodic that depends on A, of course. And in addition, these functions, this function f, this profile function f, can also be assumed even, okay? So, like in this picture, say if you think that x3 equal to 0 is somewhere here. Okay? Now, the total surface, right, can be written as the union of cells, yeah? The union of cells like in this picture, okay? I mean, the cell, I mean this guy, yeah? The guy that goes from the small next to the next, to where the next size is achieved, to the other side, yeah? This is a cell, and I will call that cell sigma k. Then the total surface sigma, I am omitting A from this notation, say sigma can be written as the union from k equal negative infinity to infinity of this sigma case. Where sigma k, by definition, what is it? Are the points in sigma that lie between two periods. Okay, this is what it meant. What it is meant. Okay, this is what this describes. Now, let me do the following. I will fix a number n. In fact, I am interested in taking large n, and consider the truncated Delaunay defined simply as the union of the sigma case from k equals 0 to n minus 1. Okay, so I pick n of these cells and I put them together, yeah, and I cut them from there to the left and from n to the right. Yeah, this is what my sigma n describes. In addition, I will consider not only the surfaces sigma k or sigma n, but also normal perturbations of it. What do I mean by a normal perturbation? Or normal graphs, I should say. A normal graph on sigma n is this surface called sigma n h. And sigma n h, by definition, is simply a perturbation along the normal by a certain function of the points at the boundary, h of x. Okay? So these are the surfaces of my interest. Here, what is nu? Nu is the unit normal vector to sigma the point x. And this h is a smooth function, which I will assume it is even in x1. I will tell you in a moment why I am assuming that. I am also assuming it is T periodic, capital T periodic, where T is the period of the Delaunay. And I also assume it is even in x3, same as the Delaunay profile. So it's just like another Delaunay profile, but perturbed. Yeah? This is what this H represents. Okay, what would I like to do? What I would like to show you, or to provide you with some intuition or evidence, is about the existence of a solution to the original problem, namely critical points with prescribed volume, but that have a form which is somewhat unusual. I would like to find a surface that looks like this. Yeah. And what does this represent? What I try to picture here is the following. If you cut the guy here and put it straight, okay, then this is supposed to be my sigma n, or my sigma n perturbed. Huh? And then what is the operation I do with that straight thing? I pick the two ends and I put them together, okay, forming a circle. Yeah, and this is what I am trying to represent. Now, I supposedly I have n of these guys, right? Yeah, and the period is capital T. Then n times capital T, yeah, is supposed to be 2 pi times the radius of this guy, yeah, the large radius. So this is the relation. This is the operation that relates n and capital R. Essentially, capital R and n are differ only by a multiplicative constant. Okay, they are two things of the same order. Okay, so what am I doing? I am translating this sigma n h to the point R times E2, and I rotate the corresponding surface in the plane x2, x3. Okay, this is the what I am describing. Now, if we want slightly more explicit expressions in cylindrical coordinates for the surface, let me consider this transformation, which is nothing but cylindrical coordinates. Okay, so x3, I put it inside here in cosine sign, and in this cosine and sine. Yeah, and what this achieves is this thing that I told you a moment ago, okay? That the ends become joined after you advance n times capital T, yeah? This is the situation. So the three-dimensional region enclosed, I will call it sigma tilde NH, okay? And this is by definition, this three-dimensional region enclosed by this sigma tilde. Remember, tilde is the twisted guy, okay? Yeah. And the thing without the twist, the straight Delaunay perturbed is this guy, sigma, but without any tilde. And well, and I do similarly with the volume, okay? The omega tilde, okay, is the transformation of the full domain omega NH, where omega NH is this guy here, yeah, which is simply the solid Delaunay region. Now, when n goes to infinity, it turns out that the volume of the two guys, okay, are more or less coincide, are very close one to each other, and they are more or less n times VA, where VA is a number which is the volume of one of the periodic cells. You can compute this explicitly. These periodic cells have volumes that oscillate between 3 pi over 4 and pi square over 2. Okay, these are explicit things. Okay, here is our main result. This is I didn't mention at the beginning. I think it's this is joint work with Monica Musso from here, Bath, and by Andrés Zúñiga from Universidad de O'Higgins in Chile. Okay, and the paper you can find in archive. Okay, so what is our result? Our result states that given a number m sufficiently large, there exists a smooth domain omega with volume equal to m, okay, which has also this special form, okay? I will describe you the form. Is a certain number. This number is large, okay? This is a large number. It's gamma to the negative 1/3, where gamma is small, and multiplied by this region omega NH, omega tilde NH, and what we state is that there exists a solution of this form that has the form omega tilde NH, so a small perturbation of omega tilde N, and multiplied by a suitable scalar, okay, gamma, in such a way that this thing here holds, okay? Okay, so remember, these are not so arbitrary things, okay? Omega is like m, it has volume m, but the specific form of omega is this scalar of this form, which is a large scalar actually, multiplied by some domain which is nothing but a Delaunay perturbed. Yeah? Okay, this is the situation. So it is a solution that has this form. If you wish, it is related to the torus of Renan-Way, but the torus of Renan-Way was substantially simpler because it was a truly two-dimensional thing, okay? Where the unknown is just a section. Yeah. Here instead there is no section. The section is variable. Okay, so this is a truly three-dimensional object. Yeah. Okay, let me discuss with you some details in the time remaining. Some details about the construction. How do we proceed to do this? First, let me discuss something I said before, which is the derivation of this of the problem, okay, by Bohr and Wheeler, essentially. First, what do we need to compute is the first variation of the energy along normal perturbations of omega, yeah, where sigma is the boundary of omega. So we consider the boundary and a small h, yeah, and consider perturbation sigma h of sigma. Sigma is the boundary of omega that has this form. Yeah. And I consider omega h is the volume, the three-dimensional region enclosed by sigma h. So in this case, what we will have is that the perimeter of omega h is by definition the area of sigma h. Sigma h is the boundary of omega h. Now, critical points of the energy subject to the volume constraint satisfied by the Lagrange multiplier rule, a relation like this. Derivative of the energy along perturbations h of the region omega, yeah, these normal graphs, but evaluated at h equal to 0, is going to be lambda times some Lagrange multiplying times the first variation of the volume itself at h equal to 0. You may wonder, well, how is this connected with the equation I showed you before for the boundary of omega? I will quickly review that. Let me observe that the Coulombian energy can be decomposed in this form after just a trivial computation. You see that this volume, the Coulombian of omega h, is equal to the Coulombian in omega plus these two quantities here. Yeah. But when you expand what these two quantities mean, yeah, you immediately see that actually what we have is the mean value of h on the boundary at main order, mean value of h, integral of h over omega, times this number, times the integral of the y over x minus y. So this is simply expanding what these two integrals mean, yeah, nothing else.
Manuel, excuse
Yes.
me, it is a misprint in the last line here. The dx.
Oh yeah, absolutely. This dy shouldn't be here. This is the sigma of x, and yeah, it's only this dy what should come. Yeah, you are right. Thank you. Thank you. Okay, and in the same way, if you expand the volume of omega, the volume of omega is simply expanded in this way. So you see the first variation of volume is this integral of h itself. So in addition, let me do the following or the same thing, but with the area. This is a computation that is well known, okay? Which is the connection between states the connection between the mean curvature and the area of the perturbed object. Okay, the area of sigma h is equal to the area of sigma plus this linear guy, yeah, which is h sigma times h integrated. Okay, and there are also lower order terms, of course, quadratic, yeah, but I will not care about them for the moment. I am considering only first variation. So in summary, taking, say, if you ignore the lower order contributions for h, then we end up with this relation, yeah? So I am simply trying to rewrite at main order what this thing means, yeah? And we find simply the integral of mean curvature times h plus this integral of h multiplied by this guy, and this turns out to be lambda times the integral of h. Then, okay, look, and here is the magic. Then if you simply take h factor of something, since this is equal to 0 for all h, then what we should have is that the validity of this relation, yeah? So this is the situation, okay? All right. Yeah, okay. Now, I will be slightly finer concerning the expansion of the mean curvature part of the operator. say, I will quickly go to the actual result. These are relatively standard things. Huh? I mean, these expansions. You can actually expand the mean curvature of sigma h by the mean curvature of sigma plus some linear term in h. And this linear term in h is a differential operator in h, defined for functions h, regular functions h on the manifold sigma. And then plus lower order quadratic terms. Yeah, this is a formula like this holds. And what is this operator, J sigma of h? Is the so-called Jacobi operator for the surface sigma. The Jacobi operator is by definition this guy. Yeah. These di's means partial derivatives in coordinates. Okay, here I am using some system of local coordinates to express this, and this is the metric, yeah, or the inverse of the metric. This is a standard computation. So this guy here is the Laplace-Beltrami operator at h, and then you see this term a squared h in addition. Yeah. And of course you have also quadratic lower order terms here, and these quadratic lower order terms can depend on first and second order derivatives of h as well. Concerning the small sketch of the proof of the theorem, it goes like this. A domain omega with volume M will solve the problem P, which is the full problem, if and only if, for a certain number gamma, the domain omega gamma given by gamma to negative 1/3 times omega, with boundary sigma gamma given by this, and mass given by this, gamma to negative 1 to m times m, satisfies this relation here. Mean curvature of the sigma gamma plus gamma times the integral of the Colombian thing of omega gamma equal to lambda for some constant lambda. Yeah. Now, this is the problem that I want to solve. What I want to find is a domain that has volume gamma to negative 1 times m, okay, and that satisfies this relation here. I need the following integral in this computation. This integral is, I call it IA. It is an integral defined on sigma 0, on one of the basic cell, okay, of a certain function f of y3, and this function f of y3 times sine theta nu 2, the second sine theta is the angular part of the torus, okay, and for the section, the angular variable for the section, and nu 2 is the second component of the normal, okay. It turns out that this integral IA is given by this quantity here. So this quantity is not depending on anything weird. It's only a function of the little f, yeah, which is the profile. Yeah, this is a computation, direct computation. What we have is that this integral IA is 0. This is actually not hard to prove. However, we believe that more than this is true, okay? What we have is that this integral IA is positive, yeah? For all sufficiently small numbers, A, next sizes, between 0 and some A star, so small for small next sizes, or for all next sizes bigger than 1/4 and less than 1/2, which is the limiting case. You may wonder what happens in between, and the question is that we do not know because we were not skillful enough to do the computation, but we strongly suspect that this integral is positive. Yeah, we simply couldn't we couldn't prove it, but we strongly believe it is true that this is positive. Yeah, you need someone more skillful to compute these explicit things. Maybe some numerically assisted thing could help on this, but we couldn't do it. Okay, so I have, but what I will assume? I will assume that this IA is positive. The main step in the proof is to establish the following thing, is that if you fix an exercise A for which this number IA is positive, then for all sufficiently large n, there exists a number gamma, which is of order 1 over log of n, and a function h, with size itself, this norm I mean L infinity, I mean C2 norm, okay? With norm of h of order 1 over log as well. So the gamma is of order 1 over log, and this h perturbation is of size 1 over log as well, such that this situation holds, okay? So we will be able to find a number gamma and a small perturbation of the domain omega tilde n, okay, such that this holds. This is the main step in the proof, proving the existence of such a solution. In fact, this is a delicate matter, and you may wonder what has this to do with the full problem. Well, this is giving you, if you wish, critical points for any sufficiently large mass. However, that mass is apparently going on a discrete set. However, if you pass from this discrete set with n things to the one with n plus 1 things, you will see that you have a gap that you can fill, okay, with the concerning the number gamma. In summary, what I am trying to say is that you will have solutions of the full problem for any little m big enough, okay, with these solutions with this shape. But this is less important. The important step is this one. So the proof is based on a Lyapunov-Schmidt type reduction scheme. Let me remind you these cylindrical coordinates in which we can express the sigma, and then we have the corresponding parametrization, okay, for the Delaunay surface given by this, and it turns out that we will have that the mean curvature of this surface sigma n tilde plus gamma times the Coulombian operator at omega tilde n, okay? The omega tilde n is the unperturbed guy without an h, okay? So if you don't include the h, will you find this formula? So the mean curvature is equal to 2. However, it is perturbed because there is some thing coming from here, right? And also from here, because this is not longer, the mean curvature is no longer constant, okay? It's not just 2, but it's 2 perturbed by something that depends on the number of balls. And in fact, you see an object like this. If you expand the two guys, the Colombian and the other guy. Here what you will see that appears actually is log of n times gamma, yeah? Times this universal constant. Yeah, and gamma times log n is a fact of life. It comes into here, and you have this certain function of x3 that I am labeling simply as f hat. Okay, then these functions f of x3 are strictly positive antiperiodic. Yeah. So for h not zero, we perturb sigma n in some h, in some little h, okay? And then I find these surfaces here, the surfaces sigma n h and the corresponding image through the cylindrical coordinates. Also, it turns out that I can expand the mean curvature of sigma n h, sigma tilde n h, in the following way, as the mean curvature in sigma n h plus these factors here, these terms here. Yeah, this is a fact. In addition, this I also discussed before. Okay, we get this guy that involves the Jacobi operator of the surface sigma n, which has this form. The Coulombian non-local operator, as I mentioned before, can be written in the form that I am describing here. Yeah? Gamma log n times integral of h is the effect of the perturbation at main order. The problem consists, therefore, in finding a function h such that for some gamma greater than 0 and some constant c, we have this the validity of this connection here. So we will use the previous computation to express the problem in a more useful manner. Yeah. It turns out that the Jacobi operator has some well-known non-degeneracy properties that are quite useful here. Invariance of the mean curvature under rigid translations of sigma implies that each component of the normal vector nu annihilate the operator, the Jacobi operator. These guys belong to the kernel of the Jacobi operator. As a matter of fact, this is the non-degeneracy assertion that any element in the kernel of J, of the Jacobi operator, can be written as a linear combination of these elements that are the components of the normal. Yeah? This is a fact. This doesn't need to be proven. It's well known. Okay? And this is the non-degeneracy property of the constant mean curvature surface sigma. In cylindrical coordinates, you can also write nu1, nu2, and nu3 as functions of x3 multiplied by cosine, sine, and and nothing. And where alpha is an even positive periodic function in x3 and beta are odd and positive. Our problem is to find a small function h. Say the full problem can be stated like this, such that this equation holds true. Yeah, I say this, all the Jacobi operator for h is equal to this error of approximation plus all this garbage here that depends on h, but defines small operators in h. Yeah, and here is the error of approximation, and here is this function of y3, capital F of y3, which is this garbage here. The functions of x3 involved are all even, positive, and t-periodic. Yeah. The operators that I am calling here, L or L1, have linear growth, and Q is a quadratic term. Yeah. So what we have to keep in mind is that these are lower order things. Huh? So to keep a main order invariant the volume, it is good to work with this constraint that the integral of h is 0, which makes the volume of sigma h equal to the volume of sigma n, essentially. Okay, main order. It turns out that we can prove by hand that there exists a test function phi or var phi such that the j of phi equals 1. Okay. Say the general theory for Fredholm alternative will tell me that there exists a periodic solution to this problem. What is less obvious is that that solution is positive. Turns out that the solution, that you can find a positive solution to this. Say something that in particular satisfies that the integral of var phi is positive. This you can see from the explicit formulas. Yeah. So the existence can be established using Fredholm alternative, but variation of parameters gives you a formula actually that allows you to find this explicitly. Yeah, as an ODE, it's the solution of an ODE. So what I have in addition is the following Fredholm alternative for H. It's an interesting Fredholm alternative, which is the following result. For any function P in S, this S guy is simply periodic and smooth and even, okay? For any function, for any reasonable function P, there exists a unique function H such that this equation is satisfied for some constants C and D. Yeah, this is the important thing. How do we find the constants C and D once we have the solution? They are explicit, simply by testing against nu2, which is an element of the kernel, and we integrate on sigma 0. and the integral for phi, for this test function phi of the previous lemma, will give me the value of d, and d is given by simply by this. Okay, it's that simple. This solution satisfies a linear operator of p, so do the scalars c and d. In fact, we have the estimate that the norm C2 alpha of this T of P, of this solution, T of P, is comparable to a constant times the norm of little p. Yeah. So it's a continuous operator. The inverse of this operator exists and is continuous. Why is this thing important? Because that will allow me to find the final result for H, which is an equation for H. Then the equation can be written in this form, where the error can be expanded in this way. And what do? What I will simply do is to test these guys against to compute the constant C and D. Okay. And so I invert the linear part of the operator projected, yeah, coupled with this relation C equal to 0. And this relation C equal to 0 gives me this guy. It corresponds to this. This problem has a unique solution, small, simply using Banach fixed point theorem, okay? And then you plug in that here in this C, and this C is something that you can indeed solve, okay? You can find a number gamma such that this guy is 0, okay? The number gamma can be computed like this at main order, okay? Here is the equation that gamma should satisfy. Observe that you have this number, this magic number I sub A that I showed you before, and some universal constant C2, which is positive. Then gamma, which has to be a positive number, is computed simply as the guy annihilating this thing here. And you need that IA is positive so that gamma is positive, okay? And this is the bottom line. So here is how we made this C equal to 0. So here is the IA, okay, and the gamma in approximate form. Okay, after this is proven, actually we use some continuity argument, continuity argument, in order to find the final result, which is the existence for any sufficiently large volume of a solution as stated here. This is how this proof goes. Here I more or less give you formally the argument, but maybe let me make for you a very light comment, okay? To conclude. In the bifurcation branch that I mentioned, yeah, as m goes to 0, you remember that's something like this, right? This is something actually that we are working together with Rupert Frank and Monica Musso, and the Borg-Wheeler left branch, stemming from mass equal to 10, gives rise to a picture like this indeed. I mean, we can find these solutions. This is what I mean, for sufficiently small mass. Yeah, and with a similar procedure as what I show you here. Okay, thank you very much for your attention.
Okay, let's thank our speaker.
Thank you.
Please, questions or comments? Okay, I have maybe a bit naive question. Since you turn to the scale where you have a small multiplier in a non-local term, yeah,
yes.
You have this gamma. You can say that if gamma is 0, you have just straight Delaunay surface. And this gamma, it works against the necklace.
I think what you are saying is correct. Yes, when gamma is 0, you only see the mean curvature part. Okay. And the mean curvature will have as a critical point, say, for instance, the infinite array of spheres. This is so at least formally, right? So no, it's that's true.
Yeah, okay. More comments? If not, let's thank our speaker again.
Thank you very much for the invitation and for your attention.
Okay.